Yeah, so this is section, we'll go over section 34. If we have time, we'll see if we can go into section, what's it, 33. But right now we'll talk about decision trees. And it's a machine learning algorithm. So it's kind of, we're gonna do a whole bunch of different machine learning algorithms these next like few sections. So I think it's kind of a really good one. Decision trees are really useful for what's called, they're a great, like I say, like they're a great beginner set of like machine learning algorithms because it's very easy to understand like what's going on. They're also really great just in practice where you can see exactly what the decisions are going on. Like, why is it making this decision versus some other more advanced stuff, which tend to be kind of like the hottest stuff right now is like deep learning. It's a lot harder to understand exactly what mistakes the computer might be making or why is it making these decisions. Which kind of decision tree kind of makes sense. And later on, we'll kind of apply this into section 35 for like ensembles, where you basically do a collection of different machine learning algorithms and apply them to make predictions and stuff. Okay, so I'm gonna go ahead and share my screen. All right, let me see here. Cool, so awesome, and decision trees. So basically, a decision tree is kind of like what you'd expect a decision. You're basically taking information and say, do you do this or do you do that? It's a supervised machine learning algorithm. So remember, supervised means that you know ahead of time what the different classifications are. So we are doing classification. You have basically some training set to say what is, what are we going to, what's it called? Like, what are the decisions we're going to do? Like, or no, sorry. What are things we're going to classify? So like, for example, a supervised machine learning algorithm say, oh, is it a dog or is it a cat? Is this fraud or is it not fraud? Is this, I don't know. Is this a high spender or a low spender in like, you know, some business case? So those are different ways you kind of like think of like classification itself. You can think of it kind of like a pathway of decisions making each one. So like I kind of wrote this little like fork in the road. I found this little things like, what do you do now? And that's essentially what's going on is that it says you have the data set and you kind of reach this point as fork in the road and say, all right, do you go left or right? And you say, okay, everyone who is this thing, go left. Everyone else, go off to the right. And you keep partitioning, going further and further and further until you make more of this kind of beautiful tree, hence decision trees. So see, they're not too bad at naming stuff. So yes, let's kind of see what this is. So you might have actually experienced a decision tree. Have you ever played 20 questions before? Yeah, so 20 questions is kind of like this decision tree. So you basically have some picture of what's in your head, right? And you just ask them a bunch of questions. So I don't know if you've ever seen this online game, Akinator or Akinator. Have you seen this before, So I'm just going to share a little bit. And so it's basically a built-in, like, you know, little, you pick something in your head. And it's like, you know, it's like, okay, like Mickey Mouse, right? Is your character a girl? It's like, oh, no, it's not a girl. Is your character exists? Well, I guess no, Mickey Mouse doesn't exist. And you can kind of keep going through here and kind of like answer these questions. Does your character wear clothes? Yes. Has your character ever been created by Walt Disney Pictures? Yes. Does your character use a sword? No. Does your character a mouse? You can kind of see Mickey Mouse Club. Yeah. No. And then soon enough, it's able to figure that out. So it's actually a pretty fun game. It's pretty impressive. Like this has been around for a while. Like I remember doing this like when I was like maybe like a teenager. Like oh, that's really cool. Like I was like maybe 12 or 13 years old. But it works the same decision. It's like basically yes or no questions. And it says, is it yes or no? And it starts classifying into what this thing is. Akinator probably is a lot better now at like making decisions because it has a lot of little questions it can ask and things. Okay, so that's an example of a decision tree. So now we can see a real decision tree and what does that look like. So I have a little like kind of practice data frame here. We see, for example, each row is a student or a person, I should say. Their work status, whether they're a student or working, whether they're, what their ages, are they young, are they old, and then favorite website A, B, or C, you know, B, A. So you can kind of see like, okay, like maybe students, for example, all like, you know, website A. And you can, for a very small data set, it's relatively easy to kind of figure this out. But you can kind of go say, if someone is a young worker, what website would you recommend? Well, you would recommend other things that other young workers would like. So you might go, okay, here's a young worker here. Oh, probably website B. Okay, and then say, what if someone's an older worker? What would you do? It's like, well, okay, here's an older person who is working website C. It's like, oh, okay, cool. So you can kind of get this kind of like flavor of like what people are doing. And this is essentially using your this would be like your training data. You already know what the answers are. And if someone comes in and says, hey, I'm a young worker, you can say, okay, let me look at like the data frame or the data and say, oh, you're likely to fit in this part. And that's essentially what decisions trees will actually do. To kind of brief summary of steps of what you end up doing, basically, you always have features in a target. So you're kind of like saying, well, what are you trying to predict? Like what are you trying to decide on? In this case, which one is their favorite website is the target itself. Your features in this case would be work status and age. And then you make a decision, a split based on some metric. So basically you say, okay, which one should I go? Do I go this direction or this direction? And we'll see this a little bit when we do a visual example. But the main point here is that you are splitting it up by some metric, and we'll actually find there's a mathematical reason or mathematical entity called information gain. And we can actually say, oh, we go either left or right depending on what gives us the most information. And that's a technical term. But then as you go down each partition, you say, okay, you do each split into further and further parts. So you can imagine, you say, are you a young person? Okay, young people, young people, young people, young people. So you would basically only look at these sets right here. And you say, is it an old or a worker? It's like, oh, well, we're only gonna get young worker. So we'd only look at these two parts. That's kind of the concept of what a decision tree is looking at. And you just keep doing this until you hit a stopping condition. So in reality, this is a nice, really clean data set. It's not like super like large. It's not also like, you can imagine if we had a young worker favorite C or favorite website is B, and another young worker whose favorite website is like C, you wouldn't know which one's which. So you actually would kind of plan this out when you're doing your training, basically designing your decision tree. This is all algorithm. Basically, you would say, well, when do you stop? You know, do you keep going in deeper? Do you make the decision at a certain point? That's what your different stopping conditions are. And this is kind of to avoid, you know, in a lot of ways, like your data is not going to be perfect. It's not going to be super clean and everything like that. One thing to note is that it's a greedy search algorithm. So it's going to make the most optimal split at that point. So we call these like greedy algorithms, where basically it's just doing whatever is the best case for it right now. So you can kind of think like, why is it called greedy? It's kind of like you eat a bunch of your cake now because you like are hungry right now, so I want to eat all the cake. And then afterwards you're like, oh, like you're like feeling sick and everything like that. Well, you're like, you didn't think of yourself for the future. You just kind of saw yourself in the now. So it's kind of like the idea of what you're doing greedy. But you'll see this a lot where it's the most optimal at that specific point. It's not looking for the optimal overall solution. Where, for example, if you wanted to join cake, maybe you have a slice every night over the next few days. And that would probably be the most beneficial, so you're not feeling sick and everything like that. Okay. Following along so far, Ella? Sound good? Cool. All right. And feel free to interrupt me if you're like, oh, I don't know what's going on. So this is actually going to be a little visual of a decision tree. And I hope I have this split up well. But basically, we'll start at the top with all the data, and we'll kind of split down depending on what things go through. So I think I'm going to try to expand my window a little bit more. Okay. So you can see here, this is all the data. And this is kind of a cool visual example. If you scroll through, basically, it's just going through some data. And it's a little sorted here, but I'm kind of scrolling through. You can kind of go through more. But basically, it's saying, okay, there's decision, or it's either San Francisco or New York. That's really what our two targets are, like whether your home is in San Francisco or New York. And then we kind of scroll through here. And then you can see basically there's a whole bunch of different aspects, how many square feet there are, what's our, what's it called? What's the price of this? And you know, they're starting to do a little extra stuff. Like, okay, like what things we can do, how many bathrooms, what's the elevation, what's the price, what's the square feet. So all these different features, okay? And now this is what the machine learning part is here. And you can see they actually are doing some correlation matrices, seeing if they are correlated between these different parts. So now this is when they actually start doing our decision tree. So now what's happening, they're just doing some more stuff. We're going to see if we're doing our first fork, and we say, okay, we're doing a bunch of if statements. To say, if it's this, go in this direction. If not, go in this direction. And so let's see what their first one is. So I think their first fork here, to the left is categorized in one way, right categorized in another. It splits. Oh, it's just telling us about the different splits. Sorry, it's talking about false negatives, false positives. Come on, show me the split. Okay, Okay, and it's going to talk about what's the best split, and then we just do recursion over and over again. I forget how long this was. All right, this is what I wanted. Okay, so now we can basically, at this certain point at elevation, basically it's saying at this certain point right here, this is basically going to be through information gain, but at this point right here, elevation is less than this amount, elevation is above this amount. So if you're less than, you go to the left. If you're greater than this elevation, you go off to the right. So you can see we're going to get some green, some blue, right? Some San Francisco, some New York. And then from here, we say, okay, price per square foot. It says, okay, this is our cutoff point. So everything that's less than this amount right here, you're going to go off to the left. If you're off to this right here, you're greater than the price per square foot at this level, you're going to go off to the right. And basically the same thing happens at this price over on this side. So you can see that we'll start kind of separating them out. And you can kind of see already before you even start, most of them are kind of like on this side. So we're getting a lot of green over on this side and a lot of blue on this side. So we kind of keep scrolling through here. They're just showing a percentage of what ends up being on each side. And we can basically keep splitting down further and further. So everyone who went on the left here, they look at year built. And this one's going to be price per square foot. So one thing that's kind of happening right now is instead of going like price per square foot for each one and then year built for each one, they're doing the one that would separate them the best in that moment. So in this case, year built will split this group as best as possible to green. So you can see here, only green is off to this right here, and only green is off to this part right here. Basically, if your price is greater than this amount, your elevation is greater than this amount, and your elevation is greater than this amount, you are San Francisco. So you can kind of see how this goes through. We kind of keep going through, scrolling, and keep splitting off further and further. And you can see, as we get better and better, we can see we get just pure green or just pure blue when we reach these points. And then if we're not quite there, we just keep splitting until we hit our condition. And then once we have this thing, we have this nice tree that kind of says, all right, if you're less than 91 feet, you are a greater price than per square foot of like 1,000. You kind of keep going down these different features until you reach the end. You're like, oh, that means you're New York. Or if you went on the other direction, oh, that means you're just San Francisco. And so what's cool now is that you have this tree pre-built, and all you got to do is take any house, and you don't know where it is, and you drop it down, and essentially you say, okay, what is the elevation? What is the price per square foot? And you basically make a decision left or right. And you can see here, they have this great visualization of these different data points, which we can see they're properly classified, saying like, this is the true label, this green and blue points, and they just go down different parts. And you can see here is that they just kind of fall in, and that way you can finally make a decision of, hey, how well does this actually go through? And you can see here, this is going to be 100%. They kind of make a thing here is because you're using the same training data. So of course it's going to be 100%. So what you want to do is actually use data that you haven't trained on, and you basically might make some mistakes. You can see here, for example, some green and blue that didn't quite make it in the right direction. But the overall thing, and you can see here, in this case, they get about 89.7%. So the point is that, you want to make sure there's no overfitting. Obviously, your training data isn't going to encapsulate every single nuance and stuff like that. There are going to be some exceptions and stuff. But the idea here is that you can get that generally about the right decisions going through. So yeah, this is actually like pretty much how the decision tree algorithm works, more or less. The biggest part we haven't talked about is how does it know when to find that split? And that's when we use information gain. But overall, not a bad algorithm, right? You're basically just making different decisions and you're splitting across each part. Cool. Yeah, so any questions so far, Ella? Sound pretty good? Yeah, seems simple enough, right? Like, that's how it always starts off. Like, oh, it seems simple. All right, so now it comes down to actually saying, how do we make this split? So these splits now actually will be based on some mathematical thing called information gain. And this is directly tied with entropy. If you had done like a chemistry or physics class, you might have heard entropy. We also have entropy in computer science and information theory. So this is where this kind of comes from. So the way I kind of describe entropy, and this is where like, you might have heard like entropy is the amount of chaos in a system. That's not actually like the best description, even for physics and chemistry. What really it is about how well you can reorganize your junk. It's like, if you can organize your stuff really well, then it means you have low entropy. Basically, it means you can describe the system with less information. So if you have, for example, all the blue balls on the left and all the red balls on the right, all you have to say is like, oh, they're like the blues are on the left and the reds are on the right, and you can describe the whole system. And that's kind of really quickly. Versus like if they're kind of like scattered about the room, you would have to describe every individual part of the room just so you can describe the whole system. So basically, you can also think of this as how many possibilities. If you have only 5 identical balls, right? Like how many different ways you can arrange those balls? There's only one way, right? There's basically, if they're identical, right? So basically you have like a red ball, a red ball, or yeah, a red ball, red ball, red ball, red ball, red ball. There's one possibility. So you can perfectly describe the system in that way. If you have 4 identical blue balls and 1 red ball, well, then there's a whole bunch of other ways to rearrange this stuff, right? So if I imagine just drawing this out a little bit, if I have my like red ball here, so I can have like a red ball first, right? I can have red ball second, I can have red ball third, I can have red ball fourth, I can have red ball fifth, right? And then the rest are just going to be blue balls like this. So you can see I have 1, 2, 3, 4, 5. Well, I guess I missed one. So like, but you get the point, is that you basically have all these different possibilities. So now what we say is the entropy of the system is larger, is that when you have 4 identical blue balls and 1 identical red ball, those now you have more possibilities, different ways to arrange them. And then you can imagine as you get more like, 3 blue and 2 red, you have even more possibilities. So your entropy is increased. There's more information you have to just use to describe your specific sets order. Like if I just, and another way to phrase this is like, if I were to tell you, I want to describe to you the order of the balls. Like it's like, okay, is it red first or blue first, and then second, what's third, and what's fourth, fifth. If I told you there's 5 identical blues, automatically, without me saying any more than saying there's 5 blues, automatically, oh, they're just a bunch of blue balls in a row. If I instead had 1 red ball, and I say, oh, I have 1 red ball and 4 blue balls, it's kind of like, okay, well, what's the order? It's like, well, I have to tell you, in this case, all I have to do is tell you where the red ball is, right? And once you know where that red ball is, the blue balls are everywhere else. If I have 3 blue and 2 red, now I have to tell you some extra information. I have to tell you where the first red ball is and where the second red ball is, and then everything else is blue. So you can kind of see is like as you get more complication in there, you have to give more information to describe the system itself. And that's really what entropy is. And that's where I kind of like, I tried my best to like make it, because this is not an easy like term for us to kind of conceptualize sometimes, but essentially it's just saying how much information you need to describe. So this leads us into information. So like I said, is that you kind of know the system already. So if we pick a ball at random, you can actually say how likely something is going to be. So for example, if they're all blue, no matter what you pick, you're always going to get a blue. You don't need to actually do the experiment. You already know. We have higher entropy when we need more information about which ball we're likely to pull out. Again, this is just another phrasing of the same stuff. Okay, this leads us to Shannon's entropy, which basically is a definition of entropy for the system. So I have a little situation here. You can imagine if we have these different scenarios: all 5 blue, 4 blue and 1 red, 3 blue and 2 red, and we go back to the situation. We say, okay, let's play a game. Let's draw a ball one at a time, and then we put it back after drawing, and we do that for a total of 4 times. And if we get 3 blues in those 4 times, we win. So we could pick like a red one, and then like pick 3 blues and we win. Or we pick 2 blues, get a red, and then another blue and we win. So, or we get all 3 blue in at the same time. So then you can say, what's the probability of winning for each of those situations? So you can kind of go through a little scenario and say, okay, what are the different possibilities and such like that? So you can kind of quantify this. And it turns out, I'm not going to go through the whole math, but basically we can go through this part and say, okay, we can actually find the probability with this equation. And it turns out we can actually use log. And the reason why we use log is so we can add them up easier. Otherwise, we'd have to basically do multiplication ourselves. So essentially, instead of doing the probability of saying, what's the probability of pulling a blue ball, what's the probability of pulling a red ball, and multiplying them together, we just take the log of that. And that way we can just add them all up. And so this ends up actually being this nice little form of Shannon's form of entropy right here. Okay. And that's really kind of just showing you like where this equation goes through. In reality, you don't have to worry too much. Also note that it's usually in base 2 because we talk about just yes or no. So log base 2 there. But in reality, it doesn't really matter because the value is going to change. it's always going to be like, no matter what log base you use, you can compare the entropies with each other. So in reality, it doesn't really matter. So if you use your normal calculator or normal np.log, that's perfectly fine. But classically, Shannon's done in log base 2. Okay, so that's kind of a whole-winded thing. You're like, cool, all right, like tell me about the system. I got an entropy, you gave me some math. What is this useful for? So this is now saying, okay, using the information, we can actually quantify before we do the split, what is the best optimal way to get the most information? And basically right here is like, well, how do we decide, make these splits? We can actually use this mathematics here, basically saying, okay, and this is a whole equation here, basically saying, what's gonna give us the most entropy or lower the entropy each time? What's gonna give us the most information by splitting this up? And we can continuously split. Note that M and N are basically just the number of occurrences each one has. Is it important for you to know this equation? Not really. This is just more to understand, like, you know, you can do this now. You can decide how much information. And once you get down, when we get to the lowest amount of information, the lowest amount of entropy, lowest amount of entropy is basically just they're all the same. So that's what our kind of goal is. Now, we might have other stopping conditions to say, well, if we try to go really far down or we don't have enough features to go all the way down, or it's not going to be perfectly split across, you can never get exactly to the lowest entropy, but you can always get lower. And if you can't get any lower, then you know you've reached the lowest entropy state that you can possibly have. Now remember, for decision trees, we're doing a greedy algorithm, so we only make the decision at that point that will split the actual entropy, will create the greatest amount of information. We are in, is it information loss? No, entropy loss. So you want to make sure that you get as much information as possible. So remember, it's a greedy algorithm. There might be more efficient ways to split this, but it's only going to look at the very beginning right then and there. The greedy part. It's going to look at this situation, say, what's the best way for me to split it right now? And it's going to split this way. But at the end, you might go through it and you're like, you know what? We should have split it in this way instead. Even though it's less entropy, it'll be easy for us later on. That's just the price we kind of pay for decision trees. But that's usually okay, because usually it's not too bad of going all the way to the end. All right. So that's kind of like how, honestly, this part on the visual introduction of how this decision tree works. The biggest part that's missing and from this kind of description is how do you split it? And the way you split it is basically you essentially use this information gain, say how much information you actually gain from each split. And that's what this equation comes from. So you can figure this out. You basically calculate this entropy, this information gain. You plug this in the formula, say, okay, we're going to split it in this way. That's going to be our decision split. And then you just keep doing that. Okay. Any questions? Sound pretty good? Thumbs up, thumbs down, silence. Okay. All right, cool. Yeah. Decision trees aren't too bad. It's just the biggest part probably is the decision split to understand what makes that decision. And it's really just essentially just math, essentially what we're doing. Okay. So last part is say, okay, now that you have decision, in reality, we don't want to just keep splitting because we'll overfit, right? If we keep splitting down to the minute part, you might actually end up incorporating something that doesn't actually exist. For example, if we keep splitting so there's only one person in that set, well, maybe that's just a fluke. Maybe that's just an outlier that just happened to be in our data set. So you might not want to do that stuff. So there's a few hyperparameters when we actually program this into it. And this is actually directly tied into decision trees on scikit-learn. And I'll show you what that code looks like in a second. But basically, you can do max depth. Basically, how many layers do you go down? So you can imagine on this visual right here, I just love this visual, that's why I keep going back to it. But you can see basically, here's the first layer right here, second layer, third layer, fourth layer, fifth layer, sixth layer. So you might not want to go 50 layers in. You might, even though you don't have it perfectly split up, you might actually want to stop it at the fifth layer. So that way you're not overfitting. So that's where your max depth is coming from. So you can specify that. You can also do minimum number of samples per leaf. And so this is right here is like a leaf. So you imagine like computer science love trees that are upside down. You can imagine if you turn that tree upside down, this right here, each little edge right here, this little spot would be a leaf or like a node. And basically saying, well, how many samples, the minimum number of samples that should be in that leaf. So if you, for example, don't set that and set to 1, that means you can have just one there. It's like, well, maybe you shouldn't just have one person. Like that seems kind of like not like it seems to be in danger of overfitting because you're like, well, I'm only counting for one person. Like that seems kind of like maybe just being a little too specific, right? So you can actually specify the number of samples per leaf. So you can say, okay, how many, like when you do the split, how many should actually go in there from your training? And then kind of similar is the minimum number of samples per split. So in this case, when you do actually do the split right here, you're saying the minimum number of samples in that leaf before your split. So if you get to a point where like your leaf has like 5 samples in it, you don't want to keep splitting it after that. So you might set up the minimum number of samples once you have that leaf in there. For example, if you set it to 5 and you have, let's say 4, or let's say, yeah, 4 in there, you don't want to split that leaf anymore. You're just going to keep it in there, even if there's some mix of green and blue together. Okay. And then the last one is just maximum number of features. So sometimes some features are not relevant to what you're looking at. Maybe it makes sense for you to just like, you know what, let's just consider the first like 5 main features. If we use all the features, we technically would get a better model for their training, but then we start overfitting. For example, if you start wanting to say, how likely is someone to cause fraud? And you start splitting and say, oh, like they're left-handed. And you're like, well, maybe there is a split that actually says from your training data that they're like less left-handed people who commit fraud than right-handed people, but that might just be a fluke of your data. That might not actually be a real feature that you want to include. So you might want to limit the number of features that you actually end up using, okay? And so with that, with these hyperparameters, basically hyperparameters means describing the algorithm from there, say what things should we consider on top of this. You can basically make a pretty powerful machine learning algorithm from decision trees. And so I'm just going to show you scikit-learn's decision tree code right here. So you can see here they have a description. Oh, actually, this is what I want to show, the classifier. So this is basically how you would write it, decision tree classifier. And then these are the different hyperparameters, max depth, min samples of split. You can see basically, that's a little description here. But you can see, I think on the bottom here, there's actually some example code. Yes, so this is basically the decision tree right here. In this case, you're just importing data itself. You, what's it called? You're importing the cross validation score. So it knows like, you know, how well is the model doing? And then here's the actual part that we really care about is the decision tree classifier. And basically you start the classifier. You can pass in a random state, basically just saying, hey, reproduce the same thing over and over again. You load the data and then you say, okay, go ahead and train it. And basically from this cross validation score, this will basically train it across, let me see if I got that right. Yeah, this will basically train this classifier to on the data, for in this case, the iris data and then the iris target itself. Okay, so yeah, that's kind of it. It's not too hard. Like you can see here, like this whole thing, which part of this, like these 2 lines are actually including, what's it called? I'm mixing up my names. This is including the data. So like really this whole thing is like, oh, you have the validation score, import the classifier. You have to actually define the classifier, and this is where you would pass in the hyperparameters. And then you just basically train it, which is this cross validation score. And that'd be it. So pretty simple. And that's what makes scikit-learn really useful for a lot of the stuff that you have. Of course, the hard part is really saying, is your data good? Is it good data? And then second, does your decision tree classifier, you have to make sure you fit the right hyperparameters. So you don't want to, excuse me, you don't want to actually, you want to make sure you don't overfit. And that's going to be the hardest part, is making your decision tree proper. Okay. So any questions?